false? The dimension of the null space of a matrix is the number of pivot columns in that matrix. False. The dimension of the null space, how do you find that? Number of free variables, yeah. So that's false. The vector spaces P2 and R3 are called what? Because they're essentially the same. Isomorphic. Isomorphic. And it's essentially the same that's very colloquial language. We'll talk about what that means in today's class. And then the last question is a free point. All right, so we're going to start today's class on section 4.4. We're going to be looking at how choosing a basis. So remember, a basis is a linearly independent set that spans the entire space. So the smallest possible spanning set. There's more than one choice of basis for any given space. But when you choose a basis, that allows us to impose a coordinate system on that vector space. And it allows us to treat all vector spaces like Rn, which is really great because Rn is really intuitive to us. We've been working with Rn for a long time. So when you are faced with questions about vector spaces that are weird, like P2 or the set of all differentiable functions, right? You can say, I don't really want to think about that. Let's just convert it to something equivalent Rn. So in order to be able to do that, we have to talk about coordinate systems. So there are two different bases I could think about for R2. The standard basis is 1, 0, and 0, 1. That is a linearly independent set that spans all of R2, meaning you can get any vector you want in R2 can be created as a linear combination of those two vectors. But there's an alternative basis. There are lots of alternative bases, but here's one. We'll call it gamma, 1, 0, and 1, 2. Those are also linearly independent, and you can create any vector in R2 as a linear combination of those two vectors. They span all of R2. Okay, so any vector in R2 can be written as a unique linear combination of the vectors in a basis. So let's look at 7, 4. If I'm going to use the standard basis, 1, 0, and 0, 1, what weight should I put on 1, 0, and what weight should I put on 0, 1 to make 7, 4? 7 and 4, yeah. That's why we call that the standard basis, because it's really easy to figure out what weights to put on the basis vectors. So this notation is the coordinates of x with respect to beta. That's how you read that. Coordinates of x with respect to beta. It is a vector of weights. So when you're asked for that, you're asked for a vector of weights. What weights should I put on the basis vectors to create the vector I was given? Okay. So in this case, it's 7 and 4. So this is kind of like, duh, right? I gave you 7, 4. The answer is 7, 4. That happens because I used a really nice basis. That's why we use that basis a lot. But there's nothing that's stopping us from using a different basis. All right, so under the coordinate mapping determined by the standard basis, the vector 7, 4 gets mapped to 7, 4. Really easy. But let's look at the alternative basis and see what happens. So I need to figure out what weights to put on the basis vectors of gamma, 1, 0, and 1, 2, to create the vector 7, 4. Anybody can figure it out just with a guess and check? 5 and 2, yeah. How would you do it if you couldn't like guess and check weights? Yeah. So it's a good way to think it through. Yeah, you know that your second entry has to be a 4. You're not getting anything out of this first vector because the second entry is a 0. So you have to create the 4 with the second vector. So it's got to be a 2. And now you've got 2 in your first entry, so you need 5 more. Right. So it's like a informal way of solving that problem. Yeah. What algebra would I write out if I was like, I don't know? What could I turn to? Yeah, I would just put in x1. I would say x1 times this vector plus x2 times this vector. I need that to equal 7, 4. And then I could set up like an augmented matrix, row reduce, and solve for x1 and x2. All right, so if I'm using my alternative basis, 1, 0, and 1, 2, the vector 7, 4, if I'm going to write the coordinates of x with respect to gamma, it's actually 5, 2. The vector of weights is 5, 2. Those are the weights that you have to put on the basis vectors to create the vector you're looking at, 7, 4. So under the coordinate mapping determined by the alternative basis gamma, 7, 4 becomes 5, 2. All right, so visually, this is how we plot things. Like, and when you're in R2, we typically use the standard basis 1, 0, and 0, 1 to plot things, and we plot multiples of 1, 0, and 0, 1. So when I want to plot 7, 4, I go 7 units in the 1, 0 direction, and then 4 units in the 0, 1 direction, and I land at 7, 4. But if I want to use the alternative basis, I would now go 5 units in the 1, 0 direction, 2 units in the 1, 2 direction, because 7, 4 was equivalent to 5, 2 with a different basis. So the 1, 0 direction, I know what that means. That's along the x-axis. But now I have a new axis, the 1, 2 axis. So I drew it in here. I just plotted 1, 2, 1, 2, 1, 2. So this is like my 1, 2 axis. And I have to go 5 units in that direction. So first I go 5 units in the 1, 0 direction, then 2 units in the 5, 2 direction, and I land here. And you can see that that lands you in the exact same spot as going 7 in the 1, 0 direction, 4 in the 0, 1 direction. Yeah. No. Yeah, good question. Typically, I will always give you whole numbers just because that's nicer to work with. Yeah. Yep. Yeah, right. Yeah. Yep. You could just take a scalar multiple to shrink. Yeah. So that's what the alternative basis means. It's just sort of different axes. Instead of using 1, 0, and 0, 1 as the directions to plot, you have different directions. All right, so here I've given you a basis for R3. Okay. I'm telling you it's a basis, so that means you know that those 3 vectors are linearly independent and they span R3, which means that any vector in R3 can be written as a linear combination of those guys. All right, I'm telling you that the coordinates of a vector x with respect to the basis beta is 1, 0, 4, and I want you to find x. So remember, the coordinates with respect to beta, that gives you a list of weights. This is a vector of weights that you would put on the basis. So this is actually a fairly straightforward question. There's very little algebra. My vector x is just, I've been given a vector of weights to throw on the basis. So I put a 1 on -2, -5, 7, a 0 on 1, -4, 4, and a 4 on my third basis vector. And I end up with -6, -13, 3. So this is sort of, these are like standard coordinates. Right, that if I was going to plot it in R3, that would be -6 in the x direction, -13 in the y direction, 3 in the z direction. 104 would be how I would plot it if I was using these 3 vectors from beta as my directions. All right, now I'm going to have you go the other way. I'm going to ask you to find the change of coordinate. Oh, sorry, it's a different question. The change of coordinate matrix from beta to the standard basis. So basically, an alternative way of figuring out what we just did would be to take my 3 basis vectors and put them in a matrix. -2, -5, 7, 1, -4, 4, -1, -2, -1, and then multiply by 104, right? Because that will give me -6, -13, 3. It's just an alternative way of writing what we just wrote. So the matrix made up of the basis vectors, this is called your change of coordinate matrix. Coordinates matrix. Because all you have to do is multiply by the matrix of weights and you get your standard weights for the standard basis. All right, so now I'm going to have you go backwards. Now I want you to find the coordinate vector given the x. So this is your standard 5, 2, 9. 5i, 2j, 9k, right? And I want you to find the coordinate vector for this other weird basis. What weights do you put on this new basis that I gave you to create this 5, 2, 9? So I'm going to put an x1, some unknown weight on my first basis vector, x2 on my second basis vector, and x3 on my third basis vector. And I need that to create 5, 2, 9. How do you solve that? Augmented matrix, row reduce. So you would your matrix would be your 3 basis vectors augmented with the 5, 2, 9. And when I solve my vector x with respect to my new basis, which I called beta, I get x1 is 0, x2 is 4/3, and x3 is -11/3. So I'm just going to jot down. If anybody goes back and reads this, they can see how we did it. -2, -5, 7, 1, -4, 4, -1, -2, -1, augment with the 5, 2, 9, and RREF. So that's sort of our go-to because it's so easy to have your calculator do that for you. I'm going to do it again another way using an inverse matrix just to remind you what inverse matrices do. You don't have to do it this way unless I specify. So basically what we're trying to solve here, if you look at that vector equation that I wrote, x1, x2, x3 are unknowns. I'm going to translate that to a matrix equation. So my matrix equation would be -2, -5, 7, 1, -4, 4, -1, -2, -1. It's my matrix A. Vector of unknowns, x1, x2, x3. And I need that to equal 5, 2, 9. So now it's written as a matrix equation. My change of coordinate matrix times my unknown weights, I need that to come out to 5, 2, 9. So to solve this, I could multiply both sides of the equation by the inverse of that matrix. So I could A inverse, multiply both sides on the left by A inverse. This guy is A. What's A inverse times A? and then I times anything is that thing. So I'm just going to have my weights. That gets my weights by themselves. And now I have to multiply A inverse, which I have to figure out what it is before I can do that, but A inverse times 529. All right, so how would I find A inverse? Do you guys remember? Augment with the identity and row reduce. Your calculator can also just find A inverse. I should show you how to do that because it's handy. Like this. I'm going to put in my 3 by 3 change of coordinate matrix. All right, so it's -2. Oh. -2, 1, -1, -5, -4, -2, and 7, 4, -1. Okay, so it's not in the math, it's not in the matrix math menu. Just quit out of there, go to your home screen. I'm going to call up matrix A just by name in the home screen. And then the notation for inverse in the real number system is to the -1, like the inverse of 5 is 1/5 or 5 to the -1. You can use that same notation in your calculator. This x to the -1 button will give you the inverse of matrix A. And then I'll hit math, enter, enter, and it gives me the inverse matrix with fractions. Yeah, you can change the decimals to fractions in a whole matrix by doing math, enter, enter. Yeah, it's handy. So then I've got the inverse matrix. And you might be thinking this takes way longer than RREF. Yeah, but I just wanted to remind you how to use an inverse matrix to solve a matrix equation. So I'm just going to write from calculator, get A inverse. You're going to multiply that by 529 and have my calculator do it without actually writing down that whole matrix. Maybe I'll store this as matrix B. Right, so hit store, go into your matrix menu. I think this is how you do it. Second matrix, store that as matrix B. Yeah, so now that's stored as matrix B. Now I'm going to go in and define 529 as a vector. Maybe I'll make it matrix C, which is a 3 by 1, 5, 2, 9. And then I'm going to multiply matrix B by matrix C. And change to fractions. 0, 4/3, -11/3. Which is what we got when we did it by row reducing. It's just another way of solving the same equation. All right, we've got one last question here. Here's where these coordinate vectors come in really handy when you start being asked questions about vector spaces that aren't real vector spaces, right? The vectors are actually other kinds of things. So I have P3, the set of all polynomials of degree 3 or less. The standard basis is 1t, t squared, and t cubed. You would just throw weights on those three things and you can build any element of P3. So I want to find the coordinate basis, the coordinate vector with respect to basis beta, the standard basis. So every element in P3 looks like A0 plus A1t plus A2t squared plus A3t cubed. So what weights should I put on my basis beta to create a generic element like that? It's not, maybe this is so easy that it's tricky, right? Yeah, A0, A1, A2, A3. There's my vector of weights that I would put on my basis beta to create any element of P3. So now that vector of weights just looks like an element from where? What other vector space? R4, yeah. So it's much easier to work with R4, and that's isomorphic to P3, based on this change of coordinates idea. So isomorphic basically means essentially the same as, acts exactly the same as, because there's, I believe it was a one-to-one mapping from P3 to R4. So this is a really handy tool when you're asked questions about vector spaces that you don't like to work with. Just change them into vector spaces that are more intuitive, answer the question in an Rn space, and then you will translate that answer back to whatever space you were asked about. All right, so that's it for the demo for 4.4. Take some time to work on the activities.